Okay, so we have the last talk of this afternoon session.
Thank you.
Yes, by Job. So whenever you want.
I would like to thank the organizers to invite me. It has been a pleasure to be at this conference. Sadly, I won't be able to stay the whole conference, but still nice to see you all and re-interact with many people. So I will be talking about path integrals and the existence of path integrals. I've decided to only show you some of the highlights because I would rather have you understand the key points and why it excites me and my collaborators, rather than show you all the details and show you all the nuances. So please keep that in mind. I will try to take you along the story and show you why I find this exciting. So this is work I've been doing with Neil Turok and more recently with Wei-Li Pen and in Dylan Zhou. Wei-Li is half in Toronto, half in Taipei, and Dylan is mostly in Toronto. So path integrals are maybe the most elegant way of understanding physics today. So for example, here you have the path integral for the standard model, and it's a beautiful theory and describes many, many different features of our universe with a single equation, which is kind of miraculous and of course due to Feynman. But the question is, do we really understand what this means? Do we really understand what a path integral is? And that's something I will be talking about. So of course you can do it for the standard model. Yeah, so I will be talking about that at length. Exactly. So another place where this arises is, of course, in quantum gravity. So Wheeler already said, well, the classical space-time should emerge due to interference of basically a path integral over superspace. So you can either write the Wheeler-DeWitt equations, or you can write the path integral, which is due to Claudio Bunster, who did beautiful work on that. And the idea is, how do you get classical space-time out of quantum foam or quantum fluctuations, and how to understand this path integral. And here I did write down a measure, but it actually is not a measure in this current form. So what are the problems? So if you read Feynman and Hibbs, the biggest book on path integrals, I would say, of the original books, and you already see that Feynman had some unease about his definition. So he basically says, well, we have a path integral, and we will be talking about that at length, but it might not be completely mathematical rigorous. And he basically says, well, even though we might not have the mathematical rigor at the moment, hopefully in the future we'll be able to do better and find a mathematically rigorous definition of the path integral. And that's basically our motivation in the current project. The reason that we care is well summarized by a quote of Terence Tao, who's a very famous mathematician who you might have heard about, maybe even interacted with him. And he basically says, well, the point of mathematical rigor is not to make everything dull. It's not to destroy all the intuition. It's to distill the good intuitions and give us the most, basically, framework and the most powerful methods to tackle complex mathematical problems. And I would say that also applies to physics. So what's the problem? The first thing you should realize is that the path integral, if it is an integral, is only conditionally convergent. And you already know this can be problematic in sums. So what does it mean for something to be conditionally convergent? It means that even though the integral or the sum might exist, the sum of the absolute value is infinite. And of course, for the path integral, that's very easily seen, because if you have an action which is real and you take the absolute value of the integrand, then you see that it's 1. And integrating over the space of all paths is definitely infinite. And this is problematic because of many reasons, but the most easy way to see it is that for these sums, the order of summations becomes important. So if you normally calculate your average grade, you just add up all your grades and you divide by the number of grades. It doesn't really matter whether you first added math and then English or did it in a different order. But here you already see that if you take this alternating sum and you reorder it a bit, you get either the logarithm of 2 or half of the logarithm of 2. So it's really important how you order the sum. And this is also for path integrals, or I should say for conditionally convergent integrals, the case. So the most important or most well-known conditionally convergent integral is the Fresnel integral. So you see here that you have this integral over e to the power I x squared. And it's of course very famous because it's very close to a Gaussian integral, and you can define it in this limit. And then you find that it's 1 plus I times the square root of pi over 2. However, if you go to higher dimensions, it's not so easy. So for example, if you take an n-dimensional version, which I write here, then you can either say, well, I use square regularizations, and I use basically squares or cubes, and let the limit go to infinity, and then indeed you get this result to the power n. But if you say, well, why not use radial coordinates, then you find this result. And this result doesn't actually converge. So for n is 2, you find that it oscillates around what you would say the correct result. For n is larger than 2, it actually diverges. So this is just the same thing we saw before. If you change the ordering of summation, if you change your regulator, you can get a completely different answer. So that's one problem which potentially arises for these path integrals. The other problem is that the measure is actually not a measure. So in mathematics, we define integrals using measure theory. So a little bit of measure theory is, well, if you want to define a measure, you need to have a sigma algebra. So what is a sigma algebra? Well, you have a set over which you would like to integrate, and then you have a collection of subsets. So it's a little bit like a topology. And if in order for this set to be a sigma algebra, it has to satisfy these properties. So you have to have the whole set, it needs to be in the algebra. And if you have an element, then you need the complement to be in the algebra. So far, so good. But you also have that if you have a set of subsets, then the union, the infinite union, has to be also in the algebra. And if this is not satisfied, then you don't have a sigma algebra and you are in trouble. Suppose you have such a sigma algebra, you can now define a sigma measure. And the sigma measure is the building block with which you define your integrals. So what you need for this measure, which is basically a way to size up these subsets, needs that the empty set needs to be 0. Well, so far so good. You integrate over nothing and you get 0. But in addition, you have this property, which is the problematic one. So if you have an infinite set of pairwise disjoint elements in your algebra, so just blobs which don't overlap, then you want that the measure of this union, which is in the algebra by this condition, is equal to the sum, the infinite sum, over the individual blobs, which is also very natural. I mean, if I have 2 buckets of water, then the sum of the buckets of water is equal to, well, the putting all the water in one bucket and measuring it. And this is the problematic condition. So you need these infinite conditions, because if you want to define integrals, and I'm really sketching it here, is what you often do is you make sorts of test functions, like a step function basically, and you define the integral using this finite sum, and then you need to take some limits, and you take a supremum in order to be able to integrate over an arbitrary function. So you basically dominate your function, or you suppress, you find a set of functions which is below a certain function which you want to integrate, and then you take this limit. And that's normally how you define integrals. So what's the problem? If you take a Lebesgue measure, then that's just what you would normally do. You take a square or you take a cube, and you just multiply the sides together and you get your measure. And that works, and that is actually a sigma measure if you have a finite number of directions. So for a finite number of directions, the Lebesgue measure satisfies all these properties. Or if you take the infinite product of these measures, you run into a problem. And this is actually very well known in mathematics, and I think many physicists are secretly aware of it. But the problem is that if you have an infinite dimensional measure and it's translational invariant, and this is manifestly translational invariant, then the measure is either 0 or it's infinite. And the way to see it is that you can take, for example, a cube, and you subdivide it in smaller cubes, and then you want to be able to say, well, I take the sum of all these cubes, and I want to take that to be equal to the whole cube. And basically, you see that 1 is equal to 2 to the power n, this smaller cube. And if you take the limit of n to infinity, in order for this thing to have hold, mu has to be going to 0, because 2 to the power n is growing. And this is a big problem, because if you don't have a measure, you don't have an integral, and you don't have a path integral. Of course, there do exist infinite dimensional measures. For example, the Brownian measure, or the Brownian bridge measure, is a very good example, which is a measure which you can define abstractly, use the Bochner-Mindels theorem, but you can also say, well, I define it in this kind of way. So it's basically the free theory, Note there is no I in here, so it's Euclidean theory, so to say. And this is very powerful, and it doesn't satisfy the translational invariance. In that way, you can define this measure, and all mathematicians are happy. However, this is Euclidean, and this is, of course, the ingredient for the Feynman-Katz formula. But we would like to do real-time path integrals, and we would like to do it the Lorentzian way. So that's where we basically start. So just as Seth described, I will be using Picard-Lefschetz theory. And since he already described a lot of Picard-Lefschetz theory, I will just touch a few points. So the idea is you start with this integral, which is highly oscillatory. And here it's a one-dimensional integral, but it also applies to higher dimensional integrals. What you do is you say, well, let me take the integrands, analytically continue that into complex planes. So I will assume analyticity of f. Write out the real part, the imaginary part. And what you can see with Picard-Lefschetz theory, with a little bit of topology, that this integral is equal to this sum, where here you see ni determines whether the saddle point is relevant. So I should say you calculate the saddle point of f, you calculate the steepest descent and steepest ascent manifold, and now you first determine which saddle points are relevant to your integral, meaning which contribute to this sum, and you find that you get a constant term here, basically measuring the imaginary part at the saddle point, and you get this integral, which is absolutely convergent because h will be the steepest descent manifold of j. So by construction, it's like a bell shape. So every integral, which is like here, basically integrates like this. It's absolutely convergent. It doesn't have any problems. So this Picard-Lefschetz business allows you to take a conditionally convergent integral and write it as a sum of absolutely convergent integrals, and that's a property I will use. So if you actually use this technique, and we applied this first to the no-boundary proposal, because there you can do all the integrals exactly, but we would like to go beyond, of course. If you now apply the same logic to this infinite dimensional integral, then the first thing what we do is we say, well, let's start with an n-dimensional integral, which is highly oscillatory. I missed an I see. If I now add a regulator, and I will let this regulator to be smooth. I want in the limit of r to infinity g to be 1. And I will assume that there are no poles, and it's basically a well-behaved regulator. And it can be a Gaussian or something resembling that. What you now can do is you can say, well, this integral is absolutely convergent, because the g ensures that it's absolutely convergent for r not being infinite. What you now can do is you can do Picard-Lefschetz theory on this n-dimensional integral, and you obtain this integral, where you integrate along these Lefschetz symbols, along the relevant saddle points, and you integrate along these steepest descent manifolds, and everything works out. But now, using the dominated convergence theorem, you can basically interchange the limits in the integrals because it's an absolutely convergent integral. And what you find is that the g disappears. So you can define these oscillatory integrals using analyticity by integrating along the Lefschetz symbols, the steepest descent manifolds of a set of relevant saddle points into this high-dimensional complex space, which is J. And if you now apply this to the continuum case, then you have to do a little bit more work because some of the things don't really generalize to the infinite dimensional case. But what we basically say is you can define this path integral in terms of this phase factor, which is the phase factor at the saddle point, and phase factor which corresponds to the Maslov phase in WKB. And most importantly, you get this measure. And this measure we define using the Wiener measure. So along these symbols, the integrand starts to behave like a free particle in Euclidean signature, or better to say, you can dominate it by such a free theory. And since it's dominated by this free theory, it inherits all the properties, the mathematical properties of the Wiener measure. And for that reason, you can actually define these path integrals in this way. So just to speed up. So let's say that you have this definition and you can actually work with it. How does it actually look in action? So in order to see this, I will have to have a toy model, and I will just remain in quantum mechanics. And a very tempting toy model is either the harmonic oscillator or inverted harmonic oscillator. But these are too simple, because if you do the path integral, then you see, oh, there's only one saddle point, and it's the trivial saddle point, so it's not generic enough. However, there's this beautiful model, which is the Teller potential. And the Teller potential goes like this, so it's a constant defined by the cosh of x squared, so it's just a bump. And this is a very beautiful potential because everything can be known. It's fully solvable. In particular, the propagator can be written in this way, where you sum over the energy eigenstates defined here. And the energy eigenstates are known in terms of Legendre polynomials. So you can calculate a propagator using these energy eigenstates completely without any assumptions, without any approximations. And what we will be doing is trying to see how we can approximate, using this Picard-Lefschetz theory on the path integral, the same results and see how it matches. So the first thing which you realize is that these path integrals, this propagator written like this, has been known in the literature for a long time, but there were kind of typos in the literature and nobody actually took the time to evaluate these integrals. And what we find if we evaluate the integral is that you get these kind of interference patterns. And you in particular see caustics. So this is the propagator at a fixed time as a function of the initial position and the final position. And it's kind of beautiful that this path integral leads to an interference pattern just like what you see in wave optics, where you consider lensing, for example. And to make it more concrete, you see caustics. And the caustics are basically organizing the path integral and the propagator neatly. So for example, if you have the potential well, then you can look at the equation of motion, the classical equation of motion, and given an initial position and a final position, you can look for the number of real solutions. So for example, here in the center, you see that there are 7 solutions, classical real solutions to the equation of motion, which leads to a contribution to the path integral. So these are saddle points along which you do have to do these integrals. And this is also what you see here, because here you have a single solution. If you go here in, then you have 3 solutions. Here you find 5 solutions. In the center, indeed, you find 7 solutions. And these blue lines are the caustics, which are separating the regions where you have different number of real solutions. You can also do it for the barrier. And then you find that you either have a single solution or you have 3 real solutions. So let's say that you fix the initial position and you let the final position move. And first you have only a single solution, then you see that 2 solutions emerge, and then you see that they here disappear again, and you are remaining with a single solution which rolls over the barrier. It's kind of nice, and I was surprised that I couldn't really find this in standard textbooks, that if you do tunneling experiments, then there are normally only 3 solutions, not 2 or not 4, but always an odd number, and it's kind of beautiful how the geometry kicks in. If you now take the propagator for this barrier, then indeed you find these caustic regions. So you can see it, for example, here in blue line. And these caustic regions, where you go from 3 solutions to a single solution, indeed order the propagator, which is the path integral we are trying to evaluate. And it's not only in the path integral, in the propagator when you make these plots, but if you actually solve the Schrödinger equation and you bounce a particle off the barrier, you can actually see these 3 solutions. And basically you can see it in the fact that you here have a multi-image region bounded by these caustics. So the green lines are the caustics, which correspond to these blue lines. And they allow you to predict qualitatively what the Schrödinger equation is going to give you. So finally, let's consider complex solutions. So far we only considered real solutions, which is a good starting point for WQB. But of course, we also would like to have complex solutions, as for example done in the no boundary proposal. So let's take the potential well, and here you see the caustic structure. This is basically for the 3 different h-bar. So you see that here you are in the quantum regime, here you approach the semi-classical approximation, the caustics get more pronounced. And what you can do is you can evaluate in blue here the absolute value squared of the propagator. So that's here in blue for this h-bar, here in blue for this h-bar, and here in blue for this h-bar. What you now can first do is you can do a WQB approximation using only the real saddle points. So the WQB approximation is just a saddle point approximation. And what you get is these black curves. So you see that in the 3 image region, or the 3 solution region, the WQB approximation does a reasonable job. So the black line starts to overlap with the blue line. However, for the single image region, it does a terrible job. It drops to infinity at the caustic, which you would expect because WQB breaks down. But afterwards, it drops just to a constant. And this is where you expect the complex solutions to become important and basically quantum tunneling to come in. So what you can do is you can say, well, let me now look for all the complex solutions to my equation of motion. And so what I've done here is I've set the initial position to be -5. And what I've done is I've screened complex initial velocity space. So I've tried all kinds of different complex initial velocities and have checked where does the particle end up if I start with this complex initial velocity. Of course, normally you end at a complex final position, which is completely useless. However, here all the green lines are the lines where the final position is actually real again. So these are potential saddle points you would like to include in your path integral. And what we find is indeed there are complex saddle points which fill this gap. And they run along this green line, so this small green line. So there are also saddle points here and there, which are completely irrelevant to the path integral. If you add them, you get something different from the exact result. But if you dig them along this green line, you find that you indeed get something which starts to resemble the exact propagator. However, then you run into a problem. After you go to a final position of 1.5, this saddle point ceases to exist. So it just disappears. And what happens is that your classical trajectory, which goes into complex plane, hits the singularity of the cosh, so the singularity of your potential. And afterwards, you are in this regime where you have passed this barrier, basically, and you just don't end up at the point you are trying to shoot to. So after 1.5, the WKB approximation, in its naive way, just fails, because the complex saddle points which you need to include no longer exist. So what you can do is you can say, well, let me see this as a branch cut and analytically continue beyond this barrier, which is this pole crossing where you hit the singularity of your potential, and then everything works again. So you see that you have, again, a WKB approximation which does exactly what you want and approximates the exact results very neatly. However, now you have to basically think deeply and philosophize with yourself, because in the region of bigger than 1.5, where you need this analytically continued saddle point, you get a perfectly good result. However, you don't get a solution to your boundary value problem. So there simply is no classical complex path which allows you to do WKB beyond this barrier. You can still do the path integral, Picard-Lefschetz theory still applies, but you just don't find a solution to your equations of motion, which interpolates between the initial and the final position of your path integral. This is something I only recently discovered and find very curious, but it's kind of neat that by studying such a very simple model, which is of course a lot simpler than quantum gravity, you already can find new phenomena which were, as far as I know, not known. So I've also studied this in the discretized theory, and it looks to be hidden in there. But if you look in detail, you still find the same phenomenon, where if you hit this branch cut, the discretized theory basically gives you false results. So this is, I think, something we should investigate further. Of course, this might be a higher order effect, which only occurs when you have complex saddle points which give you a small contribution. However, since gravity has so many singularities, it might also be, in some circumstances, an important contribution. And by just solving the equation of motion, we just might miss the whole saddle point, which is kind of mind-blowing to me. So just to summarize, interference is a leading property which is very universal in our quantum universe. It's also, of course, in classical physics important. However, the path integral, as we normally see in textbooks, is not an integral to mathematical standards. And we should care about that, because if we want to use techniques of integration theory, then it better be an integral. Using Picard-Lefschetz theory, we claim that there exists a path integral which can be defined on the Lefschetz symbols of a certain set of complex saddle points which correspond to instantons. However, it might be a little bit more subtle than you would hope, and there is the question, of course, to find which saddle point is actually relevant and which saddle point is not relevant to your theory. This is actually something, a formula which the resurgence community have started to arrive at via different means. So the derivation is different, but the result seems to be fairly similar. They basically guessed the same results, which is kind of fascinating. So we only discovered that after we did our research. It seems that instantons go beyond complex classical paths, which I find still astonishing. and would like to learn more about. And I hope that these techniques will ultimately be applicable to quantum gravity, where we can try to rigorously define the path integral for gravity and start to evaluate it in different circumstances without having to fudge anything or without having to do questionable steps. So I would like to have it very sec and try to do it step by step where we can understand all the mathematics, since we don't have a lot of observations. So in many circumstances in physics, we are allowed to make all kinds of leaps because we can subsequently test with experiments whether it works. But I think in quantum gravity especially, it's really important we try to stick very rigidly to the mathematics, because that gives a lot of restrictions to our theory, which is also fun because you can learn things which you didn't set out to learn. So thank you very much for your attention, and happy to take questions.
Okay, thank you, Job. We have some question here. I can give the mic.
Yeah, thanks, Job. I had a question about something you spoke about in the beginning, which
Yes.
is to do with the fact that you have a sigma algebra and the measure should extend to the full sigma algebra. So, just defining any integral. So in the case of, once you have the path integral, of course, now you don't have real measures. You can think of it as a complex measure.
Yes.
And in which case you do have theorems. I mean, guaranteed the complex measures extend, but if they satisfy certain convergence properties, then complex measures can extend. And so have you, in your examples, of course, where does the whole structure of the sigma algebra come in to these examples? I guess it's much simpler, but even there you have just like a Brownian path, you have the measure, you have the sigma algebra of the set of paths. So where does the complex measure come in? So
Yes. So the first thing to say is that the sigma algebra we take is just the same sigma algebra people take in Brownian motion. So that's the Borel sigma algebra over subsets. So it's like you take all paths which are continuous but not smooth, and you can say, well, I consider my algebra where I make small windows and I want the path to pass through these. So that's the algebra, and then you have the measure, of course. And what we find is that basically this is a complex measure, but it's dominated by the Wiener measure. And that's important, because if it's dominated by the Wiener measure, you can use some very elementary mathematics to show that it inherits all the sigma measure properties. So since it's dominated by this free theory, or the Wiener measure, or however you want to call it, it inherits all the properties you need in order to define integrals. So it's a little bit like the Feynman-Katz formula, but then for real-time processes.
Okay, there is a question there. Could you please?
Sumiti and I are bookending your talk. Can we look at the Pachteller at the very end?
Sure. Where?
The very last slide where you were talking about WKB. Sure, here's fine. So I just want to understand one small piece, and then I have a bigger question. You said that the WKB in the classically forbidden region, that is to the right of the caustic, you said the solution was essentially constant. Did you just mean that it was exponentially suppressed, or did you really mean it was constant?
Well, it's not strictly constant, but it looks like a constant line here.
Okay.
So the black line.
So you just mean it's exponentially suppressed?
Yeah, so WKB for only the real saddle point.
Okay. And then I'm curious about this phenomena you described of hitting the singularity of the potential. And my first reaction was that it would just be a resurgence. That is, that you're just going to continue to a different exponential branch on the other side. But are you saying it's different from that or not?
Well, no, it's exactly that. But if you start with these saddle points being solutions to your shooting problem, your boundary value problem, and now you go past the branch, and you say, oh, well, might that also apply to some boundary value problem? And the answer is no. So you have an instanton, or you have a saddle point, but you have no classical space-time associated to it. So we often talk about these saddle points as being a complex space-time, for example, and you have a Lorentzian region, you have a Euclidean region. But here you have a circumstance where there just is no space-time. There is something you can compute using analytic continuations, just like you described, which is perfectly fine as it seems. But there's just no classical path associated to it.
So, but we understand well what that resurgence is, no? That it's just, we're using exponential forms because they're easy to deal with, right? E to the I times a function is easy to deal with. It's a nice basis, but that couldn't possibly match the analytic structure of the potential. And so you're just going to a regime where you have to use another set of exponentials as your basis, no?
I don't think so, but maybe
We
we should
should
talk about this
discuss,
offline
yeah.
with the Blackboard.
Yeah.
Maybe I'm just misunderstanding what you're saying.
Any further question about this? Yes. There's one here down.
There is one thing that I didn't quite understand with this Picard-Lefschetz. You introduce a regulator, and then if you can go to that slide back again. So you introduce a regulator, and then you write the integral as a sum. Yeah. And then take the limit, and then the regulator drops out.
True.
But the sum is being defined by this, so the domain of integration basically is still being dictated by the regulator, right?
So what
So
we
it
decided
depends- So what you are summing over in the end depends on the choice of the regulator.
No, so
Right.
we took the saddle points of only F.
Oh, okay. So you.
For exactly the reason you described. And of course we choose our regulator to be featureless as possible, so to say, that it doesn't influence the structure in the intermediate steps.
Mhm.
So the point is that if you, on the left, you are not allowed to put a limit inside.
Right. Yeah,
But then
that's-
on the right you are. And that's kind of fascinating because you have now a large class of regulators which are not influencing your final result, which is nice.
Mhm. Okay. So the set of saddle points is only defined by F, not by the regulator.
Exactly.
Okay. That's what I want to know.
Okay, so thanks you, Job, again. Yes, so now we have 10 minutes. If there are further questions for all the three speakers, discussion, complaints, anything, you have all the freedom now. Well, 10 minutes freedom now. Yes, if you want to speak, two speakers come to be here in case, yes. Any other question was left? Yes.
Yes, I start by a question to Sumati. So, I don't know, everyone was citing, what Bylock said this morning, so let me do the same. Of course, he questioned, what on earth, why are you so much glued to G mu news? And it seemed to me, from the logic of your presentation, you're also very much glued to G mu news. You somehow seem to treat them extremely seriously because you're requiring, they should be approximating your, Lorentzian object. So that seems to me very much a classical way of thinking. If you take the more quantum way of thinking, is to say, okay, these whatever discrete structures you have, they are the real thing.
Yeah.
And there is where, I should, for instance, look for interesting signatures, quantum signatures, right? So
Right.
I'm slightly worried by, choosing some measure where, which you draw out of a hat, that you are forcing things to look very classical, and you may be just missing interesting quantum structures.
Yeah, so I completely agree with you. I think, and I may have misrepresented the point of view here, but this was the other side of the coin. I was trying to look for the, what did he call it? I can't remember, top up or bottom down, whichever. But definitely in the causal set approach. I mean, we're motivated by Lorentzian geometry results, but we just let go of everything, right? I mean, we have no regularity. We have a very, very discrete substructure where we say we include everything in our path integral, including things that are not like continuum. And so as you saw, there were things that, these layered posets, which are very much not like the continuum, but you want to know how they contribute to the path integral. And in some limit, and I agree that in the deep quantum regime, it doesn't have to look anything like space-time. In fact, I think, so the point was not that the dynamics should spit out something that looks like the continuum. Even in the state sum models, you have one phase that looks like the continuum, the other phase does not. It again has a layered structure, which has potentially very interesting physics in that we only know the 2D version of it, so potentially interesting physics is, of course, within quotes. But nevertheless, that's sort of the philosophy. Here the question, I think, and I seem to have missed somehow conveying this, but the point was that once you have your theory, so your theory spits out something, how do you correlate it to, say, de Sitter space-time or something that we know in the large scale? And that's why I'm trying to say that in every theory, whatever your fundamental degrees of freedom are, you will need at some point to be able to make that connection. And then the question will be, what of your fundamental degrees of freedom resemble, space-time in the large? And that will have to be a scale-dependent question. Pretty much like if your theory spat out 4 times 6-dimensional Calabi-Yau compactified space-time, if it did, then you would have to ask, well, okay, at the scales, these compactified things are really small, and so they don't appear in the world as we know. So that's sort of the broad philosophy here, is to say that the continuum approximation that we worry about in causal sets is actually something that's broadly of interest to quantum gravity. But of course, in the deep quantum regime, yes, we have nothing like space-time, and we're happy with that, and we're not trying to get rid of those structures. It's just that we want to also understand how entropy and action play out, and in one case we've seen that entropic contributions are suppressed by the action, but it doesn't mean that we get out continuum spacetimes. So I don't know if I've answered that, or we can continue.
Not fully. I mean, let me get back to the Gemian news, right? So, of course, I think it's clear that one has, one needs observables in the quantum theory, and at least for some of them, one wants to show that they have good classical limits. But it seems to me you're asking for much more by, approaching then the space-time, which maybe one could think of as a very well-functioning fiction, which
I
work.
agree. So it is a fiction. I completely agree that it's a fiction, but you want features of that fiction, just like you want features of a fluid. You want, you want viscosity. You want all of this, but viscosity is a fiction. You really have molecules running around in the substratum, and so these are good, effective degrees of freedom which you would like to recover in your theory. That's all.
Oh, there is another comment. Just throw it.
Hi. Okay. So I have a question for Seth and maybe also for Joe. So at some point you were showing the results of your of the Picard-Lefschetz theory, and you said that you were this method was selecting the Vilenking saddle points, yes. Right?
The what?
The Vilenking.
Right.
Yeah, and so you said, this is the same result that Job and collaborators obtained. Right. So, but as far as I remember, this is problematic because these saddle points lead to unstable perturbations. So I was wondering if you've been thinking about that, and what this like. Does it mean that your calculations are unstable, or?
Okay.
Yeah.
So, sure. I mean, the like the part that I talked about was about the causality violations. That was the suppression part on choosing that side. But indeed, I don't know about these unstable perturbations for the Vilenkin side. So by choosing, like, it's just like if you follow the Picard-Lefschetz, it takes you to this side of the path integral. I'm not aware of these. Maybe you have something?
Sure. So we indeed found that these leads to instabilities, and that was a problematic feature which we talked about a lot in several papers with Thomas Hertog and Hartel and Halliwell. So you should keep in mind that it's only one sign which is the difference between the two. So it turns out that you can, if you really want to, you can basically prepare your initial state to get the desired result. But then you have to ask yourself, have you really predicted anything? Because then you have basically forced the sign yourself. So our current understanding is we couldn't find any mistake in the mathematics. So maybe the no boundary proposal is not the Big Bang. So maybe there's another model which needs to be incorporated, or maybe there's a detail in the no boundary proposal which is not currently well enough understood. So that's how we basically think about it. And what is kind of good to mention is that we had a long debate with Hartel and collaborators on this, and in the end they decided to drop the path integral. So they decided, well, let's the BQB approximation be a solution to the Wheeler-DeWitt equation. So that's the way they, at the time, resolved the issue, so to say.
But so the question was more like, is this problem also a problem in the Regge calculation? And
I think you want an urgent comment about this.
Yeah, thank you. Well, this Regge approach eventually will allow us to possibly do this calculation in not in a field theoretic way, but with finite number of variables. And I do think that the problem Job discussed comes from doing it in a way where you first consider the homogeneous integral and then put perturbations on top of that. So if you are able to consider the complete non-perturbative system, then what would happen if the tensor perturbation, or if we want to consider actually anisotropies, are growing, at some point you are forced to the other saddle point. And so this instability will regulate itself in some sense. And that's what we expect to see in the Regge case. Indeed, one can already see that this competition already in the simple system between the cosmological constant term and the conformal factor term, that it depends on your boundary conditions where you end up with a saddle point. So it's, in my understanding, your result is something like, oh, you shouldn't maybe do perturbation theory in this context, rather than maybe the physics is wrong, but that's my personal interpretation. So
also an option, I agree.
Yeah, he agrees. Any other comments, question? If not, I think we can close here. We would thank again the three speakers for being here.